2023, I-Atlas has exploded into potentially millions of fragments during its passage through our solar system, according to fresh calculations from Harvard's A.V. Loeb. The interstellar visitor, which reached its closest approach to the Sun on October 29, 2025, underwent what Loeb describes as catastrophic disintegration, fragmenting into countless distinct pieces. The physics behind this conclusion is precise and quantifiable, yet it creates an extraordinary puzzle that telescopes are racing to solve before the object vanishes forever. The mathematics forces this fragmentation conclusion through a fundamental energy problem that cannot be resolved any other way. Solar radiation delivered 700 joules per square meter per second to 3I Atlas at perihelion. To produce the observed mass loss rates through standard sublimation of carbon dioxide and water ice, Loeb calculated the object would need at least 617 square miles of absorbing surface area. This translates to a sphere measuring 14.3 kilometers in diameter. For carbon dioxide specifically, the requirement jumps even higher to 20 kilometers. But Hubble Space Telescope imaging from July 2025, captured 3 weeks after discovery on July 1st, constrained the nucleus diameter to roughly 1 to 2 kilometers maximum. That creates a 16-fold discrepancy that physics cannot ignore. You cannot hide 14 kilometers of ice and rock from Hubble's optics. The telescope's resolution would easily detect an object of that size. The only mechanism that reconciles these thermodynamics is catastrophic disintegration into millions of smaller fragments, each presenting independent surface area to absorb solar radiation. The mass loss rates themselves tell an unprecedented story of violent transformation. From early August through perihelion on October 29th, sublimation rates escalated from 330 kilograms per second to approximately 2 million kilograms per second. That represents a 6,000-fold increase in material ejection. Daily mass loss shifted from sub-million ton rates to ejecting 2 million tons per second at peak intensity. These are not gradual changes that characterize typical cometary warming. They suggest explosive processes at work, tearing the object apart. Here is what contradicts basic comet behavior observed across every catalogued solar system, Comet, in astronomical databases. The object was turning bluer as it approached the Sun. Standard comets heated by solar radiation typically glow yellowish white as dust particles scatter sunlight across longer wavelengths. The dust creates a warming effect in the color spectrum. 3I Atlas shifted toward blue wavelengths during approach, suggesting metallic compounds reflecting light in ways standard icy nuclei do not produce. Loeb noted this morning that the object got much brighter than expected based on standard cometary models. Moreover, the color of the object is blue, bluer than the Sun itself. That is very surprising, because usually when there is dust around an object, it should make it red through scattering effects. The blue coloration suggests something fundamentally different about the material composition or the way light interacts with the fragments. Picture a snowball that becomes shinier and more metallic the closer it gets to a fire. That does not occur in known natural processes within our solar system. November 9th, 2025, 11 days after perihelion passage, transformed the investigation entirely through observations that defied expectations. British Astronomical Association observers Michael Butner and Frank Nebling documented imagery that did not show a diffuse debris cloud characteristic of thermal breakup. Instead of the chaotic scatter pattern physics would predict from explosive fragmentation, they photographed organized, collimated jet structures displaying geometric patterns with remarkable precision. An anti-tail formation extended 950,000 kilometers toward the Sun, defying standard solar wind dynamics that push material outward. This anti-tail phenomenon occurs when particles are released at specific velocities and orbital configurations, but the scale and organization seen here exceeded typical formations. The primary outflow stretched 2.85 million kilometers in the opposing direction, approaching double the Earth-Sun distance. This massive jet structure maintained coherence across distances that should have dispersed the material into chaos. Additional imaging resolved at least 7 distinct jets displaying geometric organization and precise directional patterns inconsistent with chaotic explosive fragmentation. Each jet maintained its own trajectory and density profile. The angular separation between jets showed mathematical regularity rather than random distribution. These patterns persisted across multiple observations, ruling out temporary alignments or observational artifacts. Debris fields from thermal stress should create randomized particle distributions following statistical mechanics. These jets showed structural coherence, as if material was being channeled through specific pathways rather than passively released into space. The organization implies either natural processes we have not encountered before, or mechanisms that require new physics to understand. Loeb calculated that maintaining 50 billion tons monthly in sustained mass loss would require either massive intact nuclei, contradicting the fragmentation hypothesis, or millions of fragments somehow retaining extraordinary outgassing capacity. Natural physics struggles with both scenarios simultaneously. The energy requirements do not balance unless the surface area expanded dramatically through fragmentation. Yet fragmented objects should not maintain organized jet structures. The trajectory measurements compound the mystery with accelerations that exceed gravitational models. 3I Atlas was accelerating beyond what solar gravity alone could explain. The object gained roughly 94 kilometers per day squared at closest solar approach, already traveling beyond 150,000 miles per hour relative to the Sun, and somehow accelerating further through unknown mechanisms. Forces do not materialize from nowhere in celestial mechanics. Every acceleration requires a source. This visitor entered detection range July 1st, 2025, spotted by Chile's Atlas Survey Telescope during routine sky monitoring. The discovery immediately marked it as humanity's third confirmed visitor from beyond the solar system, joining Oumuamua's 2017 flyby and 2I Borisov's 2019 passage. 3 detections in 8 years suggests interstellar visitors may be far more common than previous estimates indicated. The frequency implies millions of such objects may pass through the solar system annually, most undetected. By late August, the James Webb Space Telescope's infrared detectors resolved a carbon dioxide envelope spanning 348,000 kilometers, approaching lunar orbital distance from Earth. This massive coma developed rapidly as the object warmed during its inward journey. The scale exceeded predictions based on the small nucleus size. Yet spectroscopy revealed peculiarities beyond just the size anomaly. Iron to nickel proportions did not match textbook cometry profiles established through decades of solar system comet observations. The molecular fingerprint looked skewed, like a passport with correct authentication stamps arranged in the wrong sequence. Compare this visitor to its interstellar predecessors to understand its absolutely unique position in astronomical records. Oumuamua displayed no sublimation signatures whatsoever, an inert body tumbling through the inner system without gas release, despite passing close enough to the Sun to activate any volatile ices. Its complete lack of outgassing puzzled scientists who expected at least minimal activity. 2I Borisov conformed perfectly to standard cometry physics with predictable outgassing and gradual thermal fragmentation, matching models developed from centuries of comet observations. 3i Atlas occupies an impossible middle ground between these extremes. It is undeniably cometary in composition, producing massive gas and dust emissions. Yet it displays accelerations, mass loss dynamics, and jet organization unlike anything catalogued across thousands of natural comet observations. The combination of features does not fit any existing classification scheme. Loeb states explicitly that upcoming telescope campaigns will resolve the ambiguity between competing hypotheses. He frames the fragmentation scenario as viable, while acknowledging an alternative framework that remains unconfirmed speculation. The natural explanation requires the object to have shattered into millions of pieces to provide sufficient surface area for the observed sublimation rates. This fragmentation must have occurred in a way that still allows organized jet formation, which challenges conventional understanding. If standard cometary outgassing cannot parsimoniously explain the observations, including the organized jets, the sustained mass loss from countless small fragments, and the geometric patterns, then technological propulsion mechanisms enter the analytical framework as a hypothesis to test. This alternative hypothesis, which Loeb presents as unconfirmed speculation requiring verification through observation, suggests specific mechanisms. Advanced propulsion systems achieve far higher exhaust velocities than sublimation processes, requiring dramatically less propellant mass to produce observed accelerations. Where natural sublimation might eject material at hundreds of meters per second, technological systems could achieve kilometers per second or higher. Directional thruster arrays would create exactly the kind of collimated, geometrically organized jets November photography revealed. But Loeb emphasizes repeatedly that this remains a hypothesis, not a proven explanation. The data must decide. The observational window to determine which narrative reflects reality is collapsing with each passing day. 3i Atlas reaches closest Earth approach December 19, 2025, offering the final opportunity for detailed study. Hubble and Webb are conducting intensive spectroscopic campaigns through late November and December. These observations represent humanity's only opportunity for high-resolution study of this unprecedented object. The urgency cannot be overstated. Once it crosses beyond effective detection range, the window closes permanently. No future technology will catch this object. No subsequent missions can pursue it. January 2026 marks the detection threshold fade, when even our most powerful telescopes lose the ability to resolve details. Spring passage carries it beyond Jupiter's orbit into the outer system, accelerating toward the galactic void at velocities that ensure it never returns. Every spectrum captured, every trajectory measurement recorded, every image resolved now will define what humanity knows about 3i Atlas forever. Astronomers are working around the clock, coordinating observations across time zones to maintain continuous coverage. The data gathered during these 6 weeks becomes the eternal observational record. No future study will be possible. No second chances exist. Observations conducted these final weeks will determine whether the millions of fragments are natural cometary debris dispersing according to orbital mechanics or components of something requiring new physics to understand. Each night of clear skies matters. Each successful observation adds crucial data points. The distinction between natural and extraordinary phenomena may rest on subtle spectroscopic signatures or trajectory deviations measured in fractions of degrees. Loeb's calculations reveal the precise mathematical constraints that force consideration of fragmentation. In order to get that much mass out of ice through sublimation, we need a large surface area of an object. The thermodynamics are inescapable. It turns out that this is a surface area of an object that is at least 20 kilometers in diameter, much bigger than the original estimate for the size of the object. So that would mean for a natural comet that it was broken up into many pieces, such that the surface area, the total amount of surface of these many pieces, adds up to the amount of mass that we need to release. The physics problem centers on energy balance that cannot be circumvented. Solar heating alone cannot account for the observed phenomena without invoking fragmentation into countless pieces. The solar constant at 3I Atlas perihelion distance provides a fixed energy input. The observed mass loss rate requires a minimum surface area to absorb that energy and convert it to sublimation. The math is straightforward and unforgiving. Yet the organized jet structures documented on November 9th show patterns difficult to reconcile with chaotic breakup. 7 distinct jets maintaining geometric coherence while the object ejects 2 million tons of material per second challenges conventional models of how fragmenting comets behave. Natural breakup should produce expanding debris clouds with random velocity distributions. Instead, observers documented structured outflows, maintaining formation across millions of kilometers. Most observers will overlook what this geometry actually implies about the underlying physics. Thermal stress creates random distributions following Maxwell-Boltzmann statistics. These jets showed organization suggesting controlled release mechanisms operating under principles we have not identified. Whether natural or requiring new physics remains the open question telescopes must answer before the object escapes forever beyond human observation capabilities. The carbon dioxide envelope Webb detected spanning 348,000 kilometers presents another puzzle demanding explanation. Standard comets produce similar envelopes as ices sublimate and expand into the vacuum of space, but the spectroscopic signatures showed unusual iron-to-nickel ratios that do not align with typical values. The molecular fingerprint does not match typical cometry profiles from our solar system's extensive comet catalogue, built over centuries of observations. These metallic ratios matter because they trace the object's formation environment. Solar system comets show consistent iron-to-nickel ratios reflecting the primordial nebula from which our planets formed. Different ratios suggest formation in an alien stellar system with different elemental abundances. The spectroscopic anomalies provide chemical evidence of the object's interstellar origin, while raising questions about its exact nature. Loeb emphasizes that we see a fragmented object where the pieces will get separated from each other by the tide from the sun. Solar tidal forces grow stronger with proximity, potentially ripping apart loosely bound aggregates. The physics is quantifiable through differential gravitational equations. The mathematics is precise using established tidal disruption models. The implications are extraordinary, whether the explanation proves natural or otherwise. Yet that natural explanation, as dramatic as catastrophic fragmentation sounds, might be the simplest scenario, compared to alternatives that remain unconfirmed hypotheses. Occam's razor favors the explanation requiring fewer assumptions. Fragmentation requires only known physics operating at extreme scales. Alternative explanations would require new physics or phenomena not yet observed. The acceleration measurements provide hard constraints any explanation must satisfy. Gaining 94 kilometers per day squared at perihelion while already moving at 150,000 miles per hour requires force generation beyond passive solar heating. Standard outgassing models struggle to produce these accelerations from a 1 to 2 kilometer nucleus, even accounting for fragmentation into millions of pieces. The momentum transfer from sublimation has physical limits based on molecular velocities and ejection rates. Non-gravitational accelerations in comets typically arise from asymmetric outgassing creating thrust. But the magnitude observed in 3I Atlas exceeds typical values by significant factors. Either the outgassing is far more efficient than models predict, or additional acceleration mechanisms are operating. Both possibilities challenge current understanding. The timeline matters critically for understanding this encounter's significance. An object born in another stellar system drifted through cosmic darkness for potentially billions of years, maintaining its volatile ices despite eons of cosmic ray bombardment. It then entered our solar system precisely when Earth hosts technology capable of studying it with unprecedented precision. The statistical convergence of these factors alone is breathtaking. Consider the probabilities involved. Interstellar space is vast and empty. Objects traveling between stars spend millions of years in darkness. For one to arrive just as humanity develops space telescopes, spectroscopy, and the ability to track faint objects represents an extraordinary coincidence. Missing this observational window means never determining whether we witnessed remarkable natural fragmentation or encountered something the interstellar medium contains that current physics does not anticipate. 3I Atlas demonstrates behaviors that push the boundaries of cometary science in multiple dimensions simultaneously. The blue shift during solar approach contradicts expectations based on dust scattering physics. The organized jet structures defy random fragmentation patterns predicted by thermodynamic models. The mass loss rates exceed what a small nucleus should produce even with maximum surface area exposure. The acceleration surpasses gravitational models, even accounting for outgassing thrust. Each anomaly might have individual explanations, but their combination creates an unprecedented case requiring careful analysis. Hubble's November spectroscopy and Webb's December imaging will either reveal debris fields confirming natural breakup or show structural anomalies, forcing entirely new interpretations. The resolution limits of these instruments define what details we can discern. Hubble can resolve structures down to specific angular sizes at 3I Atlas distance. Webb's infrared capabilities penetrate dust clouds to reveal hidden structures. Together, they provide complementary views of the object's true nature. The disintegration is real, photographed by multiple observatories, measured through photometry and quantified through astrometry. The jets are real, documented across multiple independent observatories using different instruments and techniques. The acceleration defied pure gravitational models, with trajectory deviations calculated with precision using orbital mechanics. These are not interpretations, but direct observations. What physical processes created these phenomena will define not just what 3I Atlas is, but what stories the darkness between stars has been carrying for eons. The answer impacts our understanding of planetary system formation, the transport of materials between stars, and the frequency of interstellar visitors. Each possibility opens different windows into cosmic processes operating beyond our solar system. The telescopes are locked on target, tracking the object as it races through the solar system. The data streams are accumulating in astronomical databases. Somewhere in the spectroscopy, revealing chemical compositions, in the trajectory calculations mapping its path, in the thermal models explaining its behavior, lies the answer to whether millions of ice and rock fragments are following predictable physics, or whether something unprecedented just passed through our solar system during humanity's first moment capable of recognizing and studying it with scientific precision.